Okay, hopefully this holds. So, as usual, all of these presentations will be available online. I'm hoping to update Blackboard as much as I can after today, so it'll be ready for your review. We're going to be beginning today, ta-da, magnetism. Okay, we've gone over magnetism a little bit. Remember, it's one of the essentially two principal forms of energy that we exploit essentially in terms of using electronics. Okay, there's the magnetic field and the electric field. Okay, so there's some laws and properties and fun stuff that goes along with that. We haven't gone through this one already, right? The magnet one? Or we have or we haven't? Have you guys seen the magnet one? Right, with poles and true north and like attracts like and all that stuff. We have seen this? Okay. No? All right, let's keep going. Remember poles aligning, atoms aligning within the metal. Okay. All right, good. I thought we did that one. So we should be on to generators. Have we done this one? Moving coils within a magnetic field. I think we stopped previously at the metal, right? The magnets. Okay, cool. So generators are magnets in practice. All right, essentially moving magnets, moving magnetic fields, or moving copper within magnetic fields, one or the other, to generate voltage within that wire. Okay, so again, the principle that generators and motors and really electromotive forces as we know it today comes from either a pre-existing magnetic field, even the one that's present on the Earth, and a piece of copper moving within that field, or a piece of metal, or a piece of metal that is sensing a field in some way, right? It induces a current within this wire, and then we can see how much current and sense how much magnetism there is. Okay, so that's like another exploitation of magnetism in the magnetic field. When we have something that's moving, when we induce a moving magnetic field, for example, when we literally turn a magnet around a piece of wire, we can induce current that way too. That in a microcosm is what a generator is it's a moving magnet. Either the wire is moving, right? You can imagine this coil, this solenoid shaking back and forth, or the magnet is moving, okay, that moving back and forth. Either one will generate an electric current within that wire. The force of the magnetism that is induced by this motion will literally move electrons within the wire. It will impart a force that will cause them to drift through the wire, right? It will actually induce a pile up of electrons, and that is the voltage that we see as a result, okay? It's not really explained here, but implicit into this is, you remember why we use coils of wire, or so-called solenoids, is essentially it's just a really efficient shape for harnessing the energy of magnetism. The actual reason is that magnetic fields generate out from a wire kind of like this. It's almost like a drop in a puddle on a lake. Okay, you can imagine a 2D surface, okay, a slice, and it radiates out the RF magnetism, okay? So the same thing happens for each of these coils. Okay, see how they're all kind of line up? And so each of these forces that's going this way, it adds and makes a really big magnet and a really strong force, or can harness a strong force that way too. It's just a very kind of efficient shape for harnessing magnetism and magnetic energy. Okay, so that's why we use a solenoid or a coil of wire, okay, the same thing. Coils come in many shapes and sizes, but they afford certain advantages. One of which is that if we have a very so-called straight magnetic field, where it's very well aligned. Okay, so the magnetic field lines are very straight across our two plates, our north magnet and our south magnet. Okay, if we are to rotate or place a coil within that field, okay, if it's oriented this way, and then we turn it so it's oriented this way, okay, this is the EMF, the voltage, the electromotive force that we see as a result of that rotation, okay? And how well this field couples to this wire, okay? It's essentially like how well does it see this coil within this field, okay? So when we're at 0 degrees of rotation, it's almost like we're completely ignoring that field. It's like an antenna that's only sensitive to one direction. Okay, if we rotate it, we suddenly are, getting lots of signal. But if we rotate it the other direction, it's like we're getting nothing. It's practically invisible. Okay, but when we are perfectly perpendicular to that signal, we are in a good position to receive it. We get a large amount of force induced into that wire, like an EMF. We keep turning it. We're in the same position, essentially the same topography, the same layout of wire as we were in the original situation. We're back to 0. And something interesting happens here. When we turn it all the way the other way, effectively 270 degrees, we have a negative voltage. Okay, this is because the direction of current in our wire is now flipped. Okay, you can see the direction of this dot. Here, the direction of current that was induced into this wire is traveling through the wire like this. Okay, electrons are migrating like so. This direction, they are traveling like this. Okay, the voltage is negative. It just means the other direction. Okay, it's which is your reference point causes voltages to be negative. Okay, and then likewise back to our same original position, we're going to get 0 reception, right? 0 induced EMF. So, yeah. All right, something called Lenz's laws. There's going to be plenty of laws in this particular presentation. But the first is Lenz's law, okay, that the field induced around a conductor is opposed by an existing field. Mechanical force applied can produce energy. Okay, this is our motion produces energy law, essentially. The strength of the induced voltage, right, how good our generator is, depends on the number of magnetic lines cut by the coil. Okay, again, that is our how many field lines. Remember our magnetic field lines, they're collections of fuzzy filings. Okay, those organized into bands. Those are field lines. Okay, so if you can imagine that we have a wire, best place to receive this magnetism, the more field lines that we cross, the more magnetism we receive, essentially. Okay. The other thing is that the speed that the conductor moves through the field matters. We scale with speed. The faster our generator turns, the more power we get out of it. We say duh, but that's just kind of like this is why, mathematically. Okay, Lenz's law. All right, so there's a couple things that we can take from that. Again, it's kind of like, this is how do we optimize our generator? How do we make a good generator? So this problem, how do we optimize the problem of get as much wire in there as possible to cross as many field lines as possible? Okay, the way that we do that is that we use many turns of wire, right? We use relatively small wire rather than, huge gauges. Okay, and we use lots of coil, lots of turns. Okay. The other thing is that generators are often run at very, very high RPMs, right? It's not like 1 or 2 rotations per minute. It's like, 1,000 rotations per minute. The equation that dictates this, or at least shows the relationship of it, okay? E equals phi is that particular symbol, times n over 10 to the 8. Okay, so this is our revolutions per second, right? How fast our generator is turning. This is the number of lines of magnetic flux that we were crossing. And E will be the induced voltage, right? Or V in our usual notation. Okay, so what is the voltage that we expect to get out of a given generator or a given wire that is turning within a magnetic field? Well, that's how we can tell, theoretically. All right, so hopefully you guys should have a good understanding of this by now, right? What the literal difference in between AC and DC voltages are, alternating current and direct current, okay? Should be fair game that if I ask you for an AC waveform versus a DC waveform of a certain voltage, that you would be able to tell me what that is and draw it out and all that good stuff, okay? So if that proposition scares you, please buff up on being able to do that, differentiating between AC and DC. If you want to ask me about it, please do. But definitely critical to know. Okay. So, what is that difference? Most people don't realize it, but it's actually pretty easy to tell the difference between AC and DC because of how the current behaves in a wire. If you guys imagine that this is a transmission line, okay, some beefy piece of cable that you often see hanging over your head. Okay, those transmission lines are very, very high voltage. They're like 10,000 volts or whatever. I don't actually know what the distribution line is. They're like 10,000 to maybe even like 50,000. It's really high voltage. Well, people who work on this stuff would say that's not even that high voltage, but it's high voltage. Inside of this wire, what the cable is doing, or what the electrons are doing in AC power, is for some amount of time, they're traveling forwards. They're traveling in this direction down the wire, and then it slowly creeps down and then stops. So for some fraction of time, for some fraction of a second, actually 60 times every second, the current inside of this wire comes to a dead stop. And then, slowly and surely, it starts to accelerate in the opposite direction. Now, 1/30th of a second later, the current is headed in the opposite direction until again, it slows down and comes to a dead stop and then reverses the pattern. So it goes this way, and it swings this way, and then it goes that way, and it goes that way. So a given electron, inside of this wire is actually really not moving that much. It drifts this direction, and then it drifts this direction, and then it drifts that direction, and down again. Okay, so where electricity comes from is kind of interesting in that it's not like we're shuttling electrons from one place on Earth to another place. We're just using those as like a medium of energy transfer, okay? At some point you are probably going to have an electron consumed as heat in an end appliance or whatever, but that is like down the line. Okay, in the actual distribution line, what's happening inside of there in AC, okay, is the electrons aren't really moving that much because of this push and pull action. Okay, remember, the reason for this push and pull action is because centered around 0 volts and starting at 120 volts-ish and going to a negative 120 volts-ish is our AC waveform. Okay, so it goes down, and it goes up, and it goes down, and it goes up. That's pretty good. I'm pretty proud of that, actually. So that is our AC waveform. All right, so what this voltage means is when it's positive, this is when we are exerting a force forwards. Okay, the electrons are slowly drifting down the wire that direction. And remember, the time in between here and here is about 1/60th of a second. Okay, lights, even these, are blinking 60 times a second. We just can't see it. Our eyes are too slow. Okay. So that off time that I was talking about, remember that time where it slows down and then stops, is where we cross the threshold here. Okay, because for some blink of an eye, Again, 60 times a second, we actually are at 0 volts. We are applying 0 volts to our lights, to our motors, to whatever. There actually is no energy being transferred to them in the form of the EMF force pushing those electrons, okay? And here, during kind of like our second half, is where we start to get the negative pull. Okay, this is where our electrons start to drift backwards. Slowly at first, because there's only a low voltage that's pushing them back. But at the, negative most part of this curve, they're being pushed pretty hard back this direction. Okay, so that's how we get our ebb and our flow for AC current. Okay. DC current is much simpler. DC current, or what we often call a DC offset, is more or less just one current all the time. Okay, it'll change depending on what your demand is. Okay, so if like a light turns off, you'll go down here. If a motor turns on, it'll probably spike and then, maybe stay up here, it'll do something like that. But in direct current, it's always traveling this way down the wire. The electrons really are kind of flowing, quote unquote. Slowly, they aren't, moving light speed down the wire. They're ricocheting from one electron from one atom to the next. So it takes them a while to migrate down, even though they are moving those tiny distances at light speed-ish. But they are migrating in one direction. So this, our scale right here, again at amperage for current. Sorry, I'll switch to a marker. Amperage for current, okay, is always positive. So 0 is kind of like our bottom axis here. There isn't any negative voltage, okay? It's all positive voltage. So this might be, 2 amps, this might be 4 amps, whatever, but it's always in the same direction, okay? Negative DC voltage would just be DC voltage that's designed to be in this direction for some reason, okay? For you guys, for your most intents and purposes, you will never deal with negative DC currents. Okay, that's kind of like a theoretical thing or a thing that happens like really quickly. Like a line might go negative for like a little bit due to some weird RF effect or something like that, but that's high level stuff, right? That's like the non-theoretical outside of our physics class stuff. Right now, the simple case is DC will mostly be, some kind of positive current. And AC is the one that, we're spending some amount of time in negative current or traveling the opposite direction down the wire, okay? So here they're talking about pulsating DC, which is an interesting concept, okay? Because you can pulse DC. If we flip a DC source on for, I don't know, as fast as we control it, 10 milliseconds, 100 milliseconds, and then we turn it right off, that's a blip on our waveform. And that can look like a pulse or a pulsating DC. This is still technically direct current, okay? It's just kind of the difference between pure DC or what we call DC offset, okay? Sometimes we have a signal, okay, really common, okay, comes up all the time in the medical device space, is when we're reading a heartbeat, for example, okay, you'll have a waveform, it'll kind of look like this, but it'll have this kind of drift to it. Okay, so this space right here, see how like far off of our 0 it is right here? You would ideally kind of want it to do this, where it's very nicely spaced, it's all level, pretend each of these looks somewhat the same. Okay, really nice and easy to read. But actual data comes in, it drifts a little bit, it has like this low frequency stuff. This part right here is called the DC offset. Okay. If we removed that DC offset to have it settle on this point, okay, so it kind of settles on this line, we kind of remove that DC offset, that's another thing that we can do, okay? The difference between AC coupled and DC coupled comes up all the time. Okay, this is on like your oscilloscopes, this is on your power supplies, this is on your multimeter. This is an AC coupled signal. Okay, we only look at the AC component, the change over time. Okay, or sorry, that's not a bad thing to say. The change without the DC offset. Okay, it's like we removed the junk that it's floating on top of, and we're only looking at the changing signal. That is our AC coupled signal. Okay, DC coupled signal is where we're just looking at that signal compared to our reference. So if it's, all the way up here, we don't care, we're gonna display it as is. Okay, sometimes that's like off the screen of your oscilloscope though. If you have a signal and your dynamic signal is really low, okay, you just have a little bit of a change, but it's riding on top of this gigantic like 5-volt signal, and your little signal is just like 0.1 volts different, it's going to be really hard to measure this, because when you try to zoom in with an oscilloscope, it's going to want to focus in on this region. But if you do the AC coupling, it will shift it down, and your signal will be really easy to read. It'll just be on the center line of your oscilloscope in AC coupled mode. Okay. So all that to say that DC offset, again, kind of like the blank stuff in between our 0 point and where our signal actually begins, is a term that I want you to know. Okay, AC coupled and DC coupled, and how to use that, like I just explained, is a good understanding. Again, if you don't quite understand it, ask Google, ask ChatGPT, get a little bit more explanation until you get it, because it is important. Okay, just know that DC can pulse. DC doesn't necessarily mean pure DC, just like up there where it's a straight line all the time. Okay, like I said, if a motor kicks on, or if a big load, turns on or off, you could totally get a little spike of current, as get an inrush current as that motor turns on, or the light bulb warms up, or whatever. That happens all the time. All right, so the main components of a generator, what do we define as a generator, is such. Where we have our electromagnet, so-called field coils. Okay, this is another new term. We have an armature, our wire coils that we just talked about, our solenoids, and then our commutator. Okay, so field coils, and armature, commutator are probably the new words that we're going to learn pretty soon here. Okay, I'm actually going to look up a video for armatures, because it's much easier to understand when you see it happening in an animation.
We can easily bundle home and car insurance and save even.
This section examines commutation in the starter motor. When current flows in a conductor, an electromagnetic field is generated around it. If the conductor is placed so that it cuts across a stationary magnetic field, the conductor will be forced out of the stationary field. This happens because the lines of force of the stationary field are distorted by the electromagnetic field around the conductor and try to return to a straight line condition. Reversing the direction of current flow in the conductor will cause the conductor to move in the opposite direction. This is known as the motor effect, and is greatest when the current carrying conductor and the stationary magnetic field are at right angles to each other. A conducted loop, which can freely rotate within the magnetic field, is the most efficient design. In this position, when current flows through the loop, the stationary magnetic field is distorted and the lines of force try to straighten. This forces one side of the loop up and the other side of the loop down. The motor effect causes the loop to rotate until it is at 90 degrees to the magnetic field. To continue rotation, the direction of current flow in the conductor must be reversed at this static neutral point. A commutator is used for this purpose. In this example, the commutator consists of two semicircular segments which are connected to the two ends of the loop and are insulated from each other. Carbon-impregnated brushes provide a sliding connection to the commutator to complete the circuit and allow current to flow through the loop. Rotation commences with both sides of the conductor loop cutting the stationary field. When the loop passes the point where the field is no longer being cut, the momentum of rotation carries the loop and the commutator segments over, so that the brushes maintain current flow in the same direction in each side of the loop relative to the stationary field. This process will maintain a consistent direction of rotation of the loop. In order to achieve a uniform motion and torque output, the number of loops must be increased. The additional loops smooth out the rotational forces. A starter motor armature has a large number of conductor loops, and so has many segments on the commutator.
Okay, so all that to say,
This is a transformer. You find them everywhere. There is...
all right, so just to restate a little bit, what we said before was that when we have an armature or a, square-ish coil that is inside of a magnetic field, okay, when it's in one position, it will see 100% of the possible force coming from that field between the two magnets. Okay, but at a certain point, in order to induce magnetism, and to induce voltage, okay, in this coil, right, where we sensed we could put a multimeter on here, put one probe on here, and actually see a voltage come out of that thing that we could use for useful power if we turned a coil within a magnetic field. At some point in the rotation, we have to have motion in order to get this voltage. Okay, this coil can't just sit in this field and generate electricity like a perpetual motion machine. Okay, it has to have some sort of force that causes this to turn that will induce this voltage. Okay, that is our generator in action. Right, the armature, some force will cause this thing to move within this field. Okay, but at some point, even if this gives itself some kick, okay, because it's metal within a field, it will want to move until it is not getting that force induced by that magnetic field, okay? But when it turns halfway, pretty much exactly halfway, we are at 0% force imparted by the field. Remember, we don't get good reception when it's 90 degrees out of phase, so we say. Okay, we see very little force or very little voltage induced on our coil at a certain part in the rotation. So what would happen is that the coil would just stop dead in the field. It would kind of teeter back and forth. It wouldn't do what we want it to do, to actually kick over like a generator should, and then kind of keep going. It'll kick and kick and kick. In order to get it to kick over and keep doing that rotation, we have this thing called a commutator and a commutator ring. Okay, essentially, it's two pieces of metal with two contacts. Okay, so as the motor turns, it swaps the polarity. So then this one is ground and this one is high voltage to get it to kick over a little bit sooner. Okay, so it doesn't completely lose energy before it gets enough force to kick it back over to a relatively high voltage state again. That's what gets it to kind of carry over that motion. Okay, so that this right here, these strips, or I guess these bands, so here is one band and here is another band, are commutator bars. Okay, so at the absolute minimum, you can have just two of them, right? Like one coil and two of them that are just swapping the polarities at the right time in the motion of the motor that'll kick over. But if you have more of them, if you chop it up into bits and put a little bit of insulation between there and add more coils, you have less weak spots. So you're only at like, 75% strength when you kick over again at any given moment. Makes a much stronger motor, but a more complex assembly. But that is the reason, for example, in this video that I just showed you, why on a motor, let me see if I can bring that back.
You might know Harbor Freight.
Yeah.
You might not know is performance.
Okay, so what you guys see here, this is a commutator bar, which is separate from this one, which is separate from this one. And each one of these commutator bars are attached to one of these wires, one of these coils that's going up and into our magnet. Okay? Many coils makes a strong magnet. Many commutators makes for a not weak magnet during our motion. Okay? So what we're going to go through next is essentially different styles of commutator, different styles of armature, and how to drive this stuff. Okay, now that we know the basic connections. Okay. Oh, I hate when I do that. Slideshow, present from current slide. Okay. All right, so again, in the stripped down, most stripped down as possible sense of creating a motor, that's what we have here. One of the simplest forms of commutators is called a slip ring, where essentially you just have a ring with gaps in it that attaches to a little piece that attaches right on there and slides along as it goes over, kind of like a piece of graphite or a conductive brush. All right, so at the right times of the cycle, it will be touching this cylinder as it's traveling along, and then when the missing part comes up, it won't conduct current, obviously. It'll just be in the right part of the cycle to manually, mechanically switch over the direction of the current using these brushes. Okay. So AC and DC generators are pretty much similar. The one difference is the commutator, actually, is how we handle the voltage coming out of this and how we design our slip ring makes the voltage either always positive, kind of pulsing like this all the time in a DC generator, or we'll get our kind of proper up and down, positive and negative AC signal, okay, where just by swapping the leads at the right time and piping them into the output, we can make those different waveforms. So here, it's trying to explain how in a normal AC pulse, okay, if we were to generate an AC pulse, this is our center point, that's kind of just for reference, it's an invisible point. We would have some positive pulse, and then we have some negative pulse. And this is our 0 volt point, right? It's saying that instead of doing that, instead of generating this negative lobe, the energy that would be going into that negative lobe is instead used as a positive voltage instead. Okay, and it really is just in the way that we swap this commutator by swapping the wire, essentially which lead is the positive voltage end and which lead is the negative voltage end mid-motion. We can flip what would be a negative pulse back to a positive pulse. And we get two positive pulses rather than a positive pulse and a negative pulse, which gives our forwards and backwards motion of AC. All right, talking about, again, how can we make the best generator possible? What do? Increase the number of coils, easy. Supply commutator sections for coil sets. I actually don't know what that means. Forgive me, this is from the book. More frequent, smaller, smoother pulses can smooth out a signal. That one is definitely a good good thing to note. Okay, because remember, our ideal situation for a DC signal, keep trying to pick up the weak blue marker, is a nice, clean, relatively stable, whatever voltage, right? If it's 5 volts, we ideally want like 5.00 volts, and there's very little variation off of that. It might be like plus or minus 1% or whatever, and it'll stay like that. But the way that we're making voltages like this is with pulses in the terms of DC generators. Okay, so you can imagine that if we're averaging the voltage, okay, this is our input signal, this might be our voltage. So we're starting at 0 volts, and then we're rising up, and then we start to go back down. But then we start to go back up, and then we start to go back down, right? And then we might do more, and then it might average out, but it will always kind of have this up and down action to it, right? Because the voltage that we're accumulating over this time, or the charge that's kind of gaining into our wire, comes in these big old pulses. Okay. However, if we add more coils that are offset a little bit in the arc, we can essentially get and average more of these peaks. Okay, so now we kind of ride this level instead. Okay, so our waves will move much, the difference between our positive and negative is much smaller. Sorry, hope the difference in color is worth it. Does that make sense? Between like why having lots of pulses is better than not having lots of pulses, or small frequent pulses is better than infrequent big pulses for this kind of stuff, for getting clean power. Okay, any other questions for what we've gone over so far? All right. Okay, so I think this is the first time that we've ever actually mentioned this explicitly, although I had told you to write this down before. With this equation, I squared R, where this gets us watts. Okay, this equation is really important when we're talking about losses in a system. Okay, remember, this is power, and the other equation that we very often use for power is V times I, right? This is when you want to know like how much power your LED strip is taking, or how much power your wall wart could supply, okay? This is most often when we want to calculate watts, what we use, volts times amps, okay? But there's another, again, this is just algebra coming from this equation. If we sub out V equals IR, okay, we get IR times I, right? And then I times I is I squared R. Okay, so that's how we get that equation. The reason why it's useful is because whenever we have a wire, any wire, even the smallest ones, and we have current traveling along it, we will have some amount of that lost as heat. Okay, it takes energy to move electrons down that wire. Some of it's going to be lost in the transfer of doing that. Okay. The equation that we use to calculate that heat is I squared R. All right, there's a couple of implications of this. One is that it scales really fast with current. Okay, if we put a little bit more current in, we got a lot more loss of power. Okay. The other is that it scales linearly with resistance. Okay, so the best case scenario for transfer of electrons down a wire is having low current and low resistance. Okay, the resistance is inherent in the property of the material. That just kind of means that we make better generators with lower resistance material. Okay, that's one implication. Don't make it out of bad materials. The other one, and this will come into to play later, is that when we want to send energy down a wire with minimal energy losses, is we want high voltage and low current. I'm pretty sure I brought this up before, but this is the reason why power substations, right, like in your division or whatever, are super high voltage, right, are 50,000 volts. Why do they not run at 120 volts like the rest of the house? Why do we have that big old substation there? The reason is because we would lose an immense amount of power transferring the same amount of power using 50,000 volts than using 120 volts, okay? If we have a 50 watt system, or call it 100 watts. Okay, so we had, I don't know, like a really low power hair dryer that, you know, takes 100 watts when you switch it on. If that hair dryer was powered, okay, with 50,000 volts for funsies, it would take an incredibly small amount of current. Okay, 100 divided by 50,000. Okay, amps. So 1 over 50. 100. What's 100 divided by 50,000? Anyone? Give me a spot check. 0.002. Okay, so stick with me. 0.002. 0.002 squared. What is this squared? 0.004, probably? Yeah? Right? 0.002 squared is 0.004. Did I get that right? Yeah? Okay. So, if we transmitted 100 watts of power to our hair dryer, okay, it would take 0.002 amps, okay, 2 milliamps of power to transmit 100 watts at that crazy high voltage, right? So the energy that we transfer is how hard we push the electrons, voltage, versus how many electrons get pushed by that, right? How many is flowing through our instrument. Okay, if we assume that the line, the cable that connected our source of 50,000 volts to our hair dryer had a resistance of 1 ohm, okay, the energy that we used is 0.004 watts. Okay, that's how much we lost in the line just transmitting power to that device. Okay, this is kind of like what the company eats by transmitting power to you. This is what they're charging you for, more or less. Okay, is how they can supply the electricity for you. Okay, now let's say, let's see how much we lose if we use 120 volts instead. We don't use 50,000, but we use 120 volts. Okay, what is 100 divided by 120? 5/6, right? What's 5/6 as a decimal?
0.83.
83, oh boy. Okay, what's that squared? Be 1 point something? 0.83 times 0.83? .83 times 0.83? 0.68. Okay, cool, thank you. So, all right, so quick maths. It takes 0.83 amps to power that hair dryer. Okay, at 100 volts. Okay, so if we were to have, by the way, just a supply, right? If we were sourcing a power supply that would only run that voltage or that load, we could get away with a 120 volt at 1 amp supply. Or like if we wanted to put a fuse on this, a 1 amp fuse would probably be a good idea, because anything over 1 amp is overload, right? So that's one way we would use our typical, oops, sorry, not that equation, but our wattage equation for power, okay? But back to our loss equation, okay, so our I squared R, our current squared is 0.68, thank you very much, and our resistance is said to be 1, we're controlling that for right now. Okay, so 0.68 watts, okay, we lost. So it's the difference between 0.68 watts and 0.004 watts for the same load, okay? You guys see how much difference a voltage makes for distribution losses? This is just losses over the cable, the losses on getting the power to you, the transmission losses, okay? This is why, okay, this, let's see, times 20, yeah, 60 times energy difference, 60 times more energy is lost with this lower voltage than this higher one over the line. And that's for no good reason. If we had just used a different voltage to get the electricity down that wire, we would have a much different scenario. Okay, and 1 ohm, by the way, is very, very small. 1 ohm is like maybe 10 feet of wire. And when we're talking about actual transmission lines, those things need to run for miles, right? The ohms on that might be in the hundreds of ohms. So we're having serious power losses across all those lines, okay? If we're a generator, we also kind of have that same limitation, that we don't want to lose the power that we're generating. We've worked so hard to create it, we don't want to lose it just getting it to where it needs to go. So it behooves us to try to up the voltage as much as possible and limit our I squared R losses across the line, okay? So hopefully that explains a little bit more on I squared R power losses, and you guys will understand that a little bit more coming up in the future. Okay, so I actually referred to eddy currents before, just once before in passing, essentially. Eddy currents are really, again, the only form of current that you'll see going backwards. So this came up in my discussion with you guys on there being only one current within a wire. Okay, you guys remember this discussion? That I said, you know, in physics class example, when we are a series, it means that we have one wire and there is one current going through that wire, okay? And that one current will just be, you know, I naught whatever. This is actually not true. The reason is because the real world is complicated, right? Wires are not just simple graphics like this. They're, in fact, complicated products, okay, metamaterials. So inside of the copper that is that wire, there are currents that the majority of the electrons will be migrating down the wire, okay, in the direction of our currents that we call I naught. That is kind of like the average current of the billions of electrons that are traveling through this wire per second. Most of them are traveling in this way. And that is the visible currents that we can measure, you know, using our multimeter, things like that. However, there are also things called leakage currents. Okay, leakage currents are on the order of like microamps, okay, mu A, maybe milliamps for like higher power systems. Okay, that's the electrons that are almost like vaping off of the line. They escape into the free air. Sometimes they double back within the material and circle back around, and they just essentially generate heat. They don't use any or contribute usefully to, you know, whatever it's contributing to the load that's connected at the other end, a light bulb, a motor, whatever. It's just spinning off and generating heat, okay? This situation is called an eddy current, okay? It happens all the time, EDDY current. It is one of the major reasons why motors heat up during their operation. Okay, it's essentially displaced energy inside of the motor that's just spinning out and creating heat. That's not, doing useful work. It's work that's wasted within the motor itself. All right, so this becomes yet another thing that we can mitigate or improve in terms of motor design, generator design. How do we deal with this issue? The way that we deal with this issue is that we avoid, let's see, okay, is that we avoid large blocks of material. If we have a large continuous block of material, okay, where all the sections of the block are touching each other, this is like worst case scenario for eddy currents because they're just free to kind of do their thing, travel one direction or the other throughout this material. We have huge losses, okay? So what we do instead is we laminate the material. If we have to have a chunk of metal this big, okay, more metal means a better motor or a better generator, better inductance, right? But more material means more eddy currents. So what do? If we have to have a lot of material, what we can do is we can bust up that material into layers, okay? So in between, we create our block again, but we make it out of stacks, sheets of material. And within those sheets, we put some kind of insulator, a piece of paper or plastic that will keep those individual layers from touching each other. So any eddy currents that occur can only occur within that layer, within that one sheet, okay? That's why motors look like this. This is called laminated sheeting, okay? So see how they're actually just stacks of lines? They're stacks of metal sheets that are slightly coated so they don't actually conduct with each other when you touch them against each other. They're individual sheets that are then pressed together to make a block of metal that is exceptionally good at holding magnetic energy while not producing large amounts of eddy currents, okay? I'm actually going to skip hysteresis. It's not really important in the grand scheme of things. All right, so the next few things that we're going to be talking about is different topologies of generator, different ways to wire up a generator. Okay, the way that's common through all of these different ways is that we always have our field commutators. Okay, they're both a little bit curved like so. Okay, we have our turning armature in the middle. And then we have connections for all of these. Okay. So here I'm going to show you, for example. Okay, so here, two things to note down. Again, the names of these generators are actually important, okay, vocab terms that you guys should be writing down and memorizing. Okay, the difference is not in the black symbol here, okay? It's the same materials, our field windings here, our armature core, it's just how we're wiring them. Okay, I'm gonna actually bring the screen down for this so you can see it more properly. All right, so I'm gonna whip back for a different generator type, but we're gonna focus on this one first because it's it kind of gets the point across. Okay, so the things to be looking at here, okay, is that the top part of our armature and one of our field windings are connected. Okay, see how they have a common point up here? And both of those attach to one of our inputs. Okay, this is the input to our generator, or rather the output of our generator, right? We generate voltage on one end. If this is a DC generator, positive voltage on one end and ground on the other. If it's an AC generator, it will switch, right, 120 times a second over and over again, okay? But, so paying attention here, we see that the top part of the armature leads into this field winding, and then that leads into the other field winding, okay? And then it's common down here on the other side of the armature. Okay, so I'm going to give you guys a second to draw this in your notebooks and write down what it is. All right, so the reason why we have different topologies, different styles of generators, is that they each have their own strengths and weaknesses. Okay, literally, like you use one in one situation, another in another for X, Y, Z reasons. We're gonna get into those in a second, but be prepared to do some compare and contrast type stuff, okay? But for now, like I said, I just kind of want you to focus on what's attached to what. Okay, the things to note is that how our armature is generated. See how really one side of the armature is just always attached to here and the other side is to there. And the other thing to note is that one winds into the other, right? So the field windings are effectively connected. Okay, the field pole coils, okay, these guys connect in parallel to the armature, right? So these guys are both connected to, parallel to the armature. And the output current varies according to the load. Okay, so a bigger load or a smaller load will affect how much current our generator is capable of creating. Okay. However, the field flux, okay, how much our signal varies relatively little. Okay, so output voltage is relatively stable, which is pretty nice. However, big downside, the terminal voltage drops rapidly when we overload the machine. So again, it's very tentative or very sensitive to the voltage or to the load that's applied, even if the field flux varies very little. Okay, so here we have a very different topology. We don't have the parallel connection, right? So here the armature and the field poles are both connected to our output. Right here, they're connected in series instead. Okay, it's our armature and then it's our field winding. Okay, so everything's in series here. Armature, winding, winding. Here, it was terminal, goes to the armature and the winding. Negative side goes to the terminal and the winding. Okay, see how that's essentially totally parallel? They call it a shunt generator, but this one is effectively the parallel generator, right? Call this one the series generator, and it very much is so. Okay, where the field windings are in series with the armature. So this one, the voltage that it outputs, as opposed to our parallel generator, is not as stable. Okay, but as the load increases or decreases, so does the load. Wait. As current increases or decreases, voltage greatly increases or decreases, not practical if load varies. Right, but it can still readily, the current that it can provide is still readily available, essentially. Okay, so we have our first generator, our shunt generator, or our parallel generator that's really good at supplying stable voltage. We have our series generator that's really good at supplying stable current. Well, what do? We combine the two. Okay, so it's our compound generator. Uses a combination of the two for series and shunt or parallel windings, which both add to the field strength and reduce ripple effects in the output voltage, right? So It has a little bit of give to it, where as the load changes, the voltage won't suddenly drop, rise or fall. But it can still deal with the power demands of the system. We have a few other generator types. Again, this is in gold for flashcards. This chapter and the next chapter coming up, I think. If you guys like flashcards, I would really recommend using them because there's a lot of vocab where it's like undercompounded generator, and then you'll need to know that decreased voltage at full load rather than an overcompounded generator which increases output voltage at full load. Okay. Again, I want to give you guys a little bit, note that down for later. Any of you guys know what Quizlet is? Yeah? Cool. Anyone not know what Quizlet is? No? Okay. Quizlet, write it down for you. Quizlet got me through college, I think. It is essentially ready-made flashcards, or you could just make your own, super easy. App-based, phone-based, computer-based. Quizlet.com, not sponsored. Really, really, really recommend that for remembering all these terms and definitions, because especially these generators, unless you figure out mnemonics or something, they can be difficult to remember which one's which. And again, totally fair game that on a quiz or a test or a final, that'll ask you which one is an undercompounded generator, or you'll have to match, definitions to words, things like that, okay? Be forewarned. Okay. I'm not going to belabor the point too much, but what you guys should know coming up is talking about efficiency and regulation. Okay, when we're talking about regulation, we're talking about how well are we keeping something at a set point. Okay, if we have a voltage that we expect to be generating, how close to that voltage are we sticking as a percentage? Okay, that is our regulation percentage. It's the ability of a system to cope with a load really changes when there's nothing attached to it. When it's a generator that's effectively running nothing versus a generator that is really struggling, right? Under full rated load, whatever it's rated for, its efficiency, how well it can regulate the output, can change substantially. Okay, so very, very often you will see no load efficiency or no load regulation and full load or efficiency or full load regulation. Okay, and how well it can deal with it over that range is, talks to the efficacy of the motor or the generator. All right, so we've already kind of talked about this, but the output voltage, right, the voltage that we get out of our generator scales with field strength. Okay, so that would be in Tesla, or B, actually. Just so you guys know, a reminder, B, capital B, in math problems is like the force of magnetism. Okay, it's often derived in Tesla. Okay, so essentially the voltage that we get out of it scales with the magnetism that we put into it. Okay, the amount of current that we can get out of the system varies inversely with resistance. That's just Ohm's law. Of course, we already know that. The device that varies with resistance also varies the voltage output of the generator, right? Again, it's just the consequence of Ohm's law. Nothing should be too surprising on this graph. I'm actually going to skip this one. All right, so here's where we're going to kind of break down more into the actual cycle of AC, or alternating current. I've spoiled this a little bit in my whole explanation about AC versus DC, but I just wanted to preface the slides that are coming up. But really the things to note, the things to keep in mind that we're really going to break down here, especially in the later chapters, is that voltage and current can be decoupled. Okay, I'm trying to figure out how to do this. So both of them vary with time. Okay. So as our voltage goes up and down and up again, this period will be 1/60th of a second, right? Okay. So during this, positive pulse will be at like, positive 120 volts, and here we'll be at negative 120 volts. Okay, what I want you guys to understand is that our current, right, the amount of electrons that we induce in that wire based on this force that we impart, that moves as a result, will also change more or less in time. Okay? And the proportion, right, how much current for how much voltage is resistance. I don't know if you guys, any light bulbs just went off there, but that's another kind of implication of Ohm's law. Okay? And so here is like our I max, our maximum current happens at this spot in the curve. And same here for I min, because that will be traveling in the opposite direction, right? So current will travel here for a little while, it will move slowly, then it'll move more quickly, and here it's moving, essentially the maximum number of electrons per second are being moved, and then a little bit less, and a little bit less, and a little bit less, until none are moving anymore, and then they start moving in the opposite direction. Okay? Oops, still this way, but less forceful, and less, and less, and less, and less. Okay, does this make sense, this concept of moving backwards and forwards in a wire? Okay. All right. So again, this is at 60 cycles per second, or hertz, right? You could say that the frequency of this signal is 6 hertz. Okay. Do I want to go over that? Yeah, I won't go over that. Okay, this stuff is important. The other stuff that I've passed not so much. This stuff is very, very important. Okay, it describes relationships. Okay, we have a few new terms. They say E, I'm going to say V. Okay, don't get confused. The average voltage is equal to 0.637 times the max voltage. Okay, and same for the I average is equal to 0.637 times the max. Okay, so what they're describing here, let me redraw my chart. Here's our 0 volts center point. Okay, so here is our voltage going up and down. Okay, so the average voltage, okay, the average voltage is this Vmax times 0.637. Okay, it's kind of like where this settles out to, the average is this number. Okay, likewise for the current, that occurs over that same interval, right? The amount of current that flows as a result of that voltage, okay, also can be talked about in terms of its maximums, minimums, whatever. Okay, this is just the maximum in one current direction or the other. Okay, and that is the same thing. So the way that you convert Imax or Vmax into average is with our magic 0.637 number. Okay. We have one more term, which is the effective value. All right. RMS is a difficult thing to understand. I'm going to play a video next, actually, that explains this better. But I just, for now, want you guys to note down this rule of thumb. Okay. EF equals max, blah, 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 blah. Okay. I'm going to give you the concept of it in a second. Man.
We're going to talk about RMS value of AC circuits. RMS stands for root mean squared. And when dealing with AC circuits, it tells you the average power dissipation that would be equivalent in a DC circuit. So on the left, we have a...
So I want to lay the groundwork for this for a second. It's actually a bit of a fool that when we say 120 volts, that we actually mean 120 volts. Fun fact. Did you know that the actual maximum voltage that comes out of a wall outlet is more like 144 volts? It's because 120 volts is actually the RMS value. In AC systems, we work with RMS values, or root mean squared values. It's kind of like converting AC stuff to DC systems. It's why we can say 120 volts or wattage from one system is equivalent to wattage in another. It's because the volts that we use is not raw volts. It's VRMS, or V root mean squared. So that's why we can compare AC systems and DC systems so easily. So that's why he's going to explain this like this in a second. But I just wanted to say that when we say that we work with 120 volts in our system, that's actually a lie, is that it doesn't go to positive 120 volts and negative 120 volts. If you measured it with a multimeter attached to a ground reference, it would actually go to something like 144 volts and negative 144 volts. And we'll explain more about that in a second.
Video, we're going to talk about RMS value of AC circuits. RMS stands for root mean squared. And when dealing with AC circuits, it tells you the average power dissipation that would be equivalent in a DC circuit. So on the left, we have a 30 volt DC power source applied across a resistor. Now the power dissipation across that resistor is going to be V squared over R. That power dissipation is going to be the same if we apply an AC signal with a root mean square value of 30 volts. Now you need to understand the difference between the peak voltage and the RMS voltage. So the signal will look something like this. We would have a sine wave with a peak voltage that is higher than 30 volts. To calculate the peak voltage, it's going to be the square root of 2 times the RMS, or the root mean square voltage. In this example, the root mean square voltage is 30. So it's going to be 30 times the square root of 2. The square root of 2 is about 1.4142. If you multiply that by 30, you're going to get a peak voltage of approximately 42.4 volts. So that's the maximum voltage of this AC sine wave. As you can see, it's not the same as these two numbers. So to get the same power dissipation across this resistor, you need to use the RMS voltage of the peak voltage, and that is 30 volts. So that's why it's important to understand how to calculate the RMS.
All right, so I'm going to redraw this one more time to kind of drive this point home. So again, imagine we had two situations. It's the same circuit. Okay, we have a power supply, plus and minus, okay, that is attached to a resistor. Perfectly resistive, no capacitance, no inductance, okay? This power supply can either be AC or DC, okay? We're gonna put the same voltage on either way, okay? How should I explain this? All right, ideally, we're gonna measure the heat coming out of this resistor. Okay, how much energy are we putting into this resistor can be measured in a temperature, right? How hot does that resistor get, essentially? Okay, so we want to understand what voltage, we heat it up, all right? We use some DC voltage, okay, that looks like this. Okay, say we put like, 9 volts on there, okay? And at 9 volts, we get 9 watts of heat out, okay? So that looks like this. So we have a stable voltage, okay? And then for that stable voltage, some amount of current will flow as well, right? This is our voltage, this is our current. It's not changing, it's kind of the same no matter what. To get the power, this 9 watts that we calculated here, for every point on our chart, we look at what the current is and multiply by the voltage, right? Where our power equals volts times amps. So volts times amps, volts times amps, volts times amps, for each instant in time, right? And then we get our average power, which we come up to say 9 watts, okay? But AC doesn't work like this, okay? So we're trying to figure out, sorry guys, I'll shift this up. Okay, we're trying to figure out in the AC waveform now. So here is our 0 point, sorry, I should be drawing this crosswise. So now our signal goes like this, right? So we want to figure out how high does this V peak need to be in order to give the same amount of energy delivered to our resistor. So it'll heat up the same amount. So it'll heat up 9 watts worth, okay? But that's a tricky problem because again, the definition of heat is this voltage times this current at this instant in time, and this instant, and this instant, and this instant, and it's constantly changing, right? So we're really kind of measuring like what is the area on that curve, or every point we're gonna do that multiplication. Okay, so it's a complex math problem, right? It's like, what does this need to be? What do we need to fudge this number to be so the current is high enough that we get 9 watts delivered to that device, okay? Well, it turns out that they did that experiment over and over and over and over again and figured out that voltage. So they figured out that, okay, for a DC 9 volt system, for an AC signal running at 60 hertz frequency, we need to take 0.637 times that to get that voltage, okay? Or we could just use that system all the time. Instead of talking about actual volts, we'll just always call volts in AC the RMS voltage. And then now we're back to 9 volts again, Okay, but that's 9 volts RMS. Okay, so now 9 volts AC and 9 volts DC agrees again because of our little fudge factor here between RMS and actual peak volts. Okay, does that make sense? Please tell me if it doesn't. Okay, are there any questions? Any at all? Okay, all right. All right, so I'm going to keep the video rolling, but I just wanted to explain the difference, that really the target is how do we make these two systems agree? How do we kind of fudge the numbers a little bit so that when we're talking 9 volts in one and 9 volts in the other, we're still talking the same energy delivered at the end of the day, okay, to make things more simple. This is how VRMS is born and used. So when we're in AC, when we're talking about stuff coming out of the wall, when we say 120 volts, you shouldn't be surprised when you actually see a maximum of 140 something volts coming out of the wall, because that's what it needs to deliver the same amount of energy as a DC load. Okay, it's not on all the time. It can't deliver the same amount of energy.
Given the peak value, because the RMS value tells us what the equivalent power dissipation would be to that of a DC circuit. So we said that the peak voltage is equal to the square root of 2 times the RMS voltage. If we divide both sides by the square root of 2 and reverse the equation, the RMS voltage is going to be the peak voltage divided by the square root of 2.
That's this number, by the way.
If we multiply the
That's where we get
by the square root of
0.637 from, is the root 2.
we get the RMS voltage is equal to the peak voltage times the square root of 2 over, multiplying these two, that's 2 times 2, that's 4. The square root of 4 is 2. So this is another way in which you can calculate the RMS voltage given the peak voltage. But where do we get this number? The square root of 2 over 2, where does that number come from? We're going to talk about that shortly. But here's the decimal value of this number. The square root of 2 over 2 is approximately equal to 0.7071.
So that was for our,
how we can get this value.
I'll whip back to our presentation in a second.
So here we have an AC sine wave with a peak voltage of 1 volt. If the peak voltage is 1 volt, that means that the RMS voltage is going to be the peak voltage divided by the square root of 2. So 1 divided by the square root of 2, that's going to be 0.7071.
All right. So I have a feeling this is going to get a little bit math heavy. That's handled in the chapter. I'm going to leave it for the reading. I'm going to put on one more video related to this, and we'll keep chugging, okay?
Hey Meta, is energy conservation...
And not give Facebook an ad. There we go.
Did you know that the voltage of the electricity in your home undergoes rapid changes? This is because the electric current alternates its direction continuously, creating what we call alternating current. If you were to graph the voltage over time, it would resemble a wave-like pattern, similar to a sine graph in trigonometry. Hence, we refer to this waveform as a sinusoidal wave.
They've mentioned 50 times per second because they're probably European. It changes 50 times a second rather than 60.
Canada and the USA, or 230 volt in places like England or India. What do these numbers signify when the voltage is in a constant state of change? You might assume that the voltage number represents either the highest peak or the average it reaches. However, that's not exactly the case. Enter RMS, root mean square, a fascinating concept used to measure voltage and current in AC electricity. Observing this basic circuit, there is a light bulb with resistance R. Once a direct current power source is connected, the bulb illuminates. To determine the current flowing through the circuit, we apply Ohm's law. Current equal to voltage divided by resistance. By rearranging this equation, we can compute the voltage is equal to current times resistance. Let's assign numbers to these two equations for reference. If we create a graph depicting both the voltage and current for the bulb, it will result in a straight line. You see, with direct current, both parameters remain constant throughout. Therefore, to determine the power consumption of the bulb, we simply multiply the voltage by the current. Simple, right? This represents our third equation. We can take the third equation and the first one to derive a new equation. Power equals the voltage squared divided by the resistance. Similarly, using the third equation with the second one allows us to derive another new equation. Power is equal to the current squared times the resistance. Keep these in mind. These two equations will be utilized later. Now, imagine a circuit using alternating current. Typically, we determine power by multiplying the voltage and current. But here's the twist. Both the current and voltage change in wavy patterns over time. So, how do we find the power now? We can multiply the voltage and current at every moment, creating a graph of the power. This power graph also oscillates in waves. Keep in mind, even if the voltage or current goes negative, the power is always positive. Examine these graphs. Voltage, current, and power all undergo continuous changes in AC systems. However, for calculations, we require some fixed values. How do we achieve that? Here's a simple trick. If we calculate the average power over one full cycle, it's consistently half of the peak power.
Get mechanic training at Universal Technical Institute and learn the skills and
What's the peak power? It's the highest value of voltage multiplied by the highest value of current. In essence, the average power in an AC system is always half of the peak power. Furthermore, the peak power is equal to the product of the peak voltage and the peak current. This relationship is crucial for understanding and calculating power in alternating current circuits. Returning to the circuit, we understand, according to Ohm's law, that despite the varying voltage and current, the ratio between voltage and current is consistently equal to the resistance of the light bulb. Let's rearrange the formula to express current as the subject. Now armed with three equations, let's endeavor to simplify them. Firstly, employing equations 2 and 3, we can articulate the peak power in terms of peak voltage and resistance. This represents our fourth equation. Subsequently, utilizing equations 1 and 4, we can formulate the expression for average power using voltage and resistance. The average power of an AC power circuit is equivalent to the squared peak voltage divided by twice the resistance. Let's revisit equation 3, rearrange it, and express the peak voltage in terms of peak current and resistance. Utilizing equations 2 and 3, we can then articulate the peak power using peak current and resistance, establishing our fifth equation. Now, employing equations 1 and 5, we can formulate the expression for average power using current and resistance. The average power of an AC power circuit is equal to the squared peak current multiplied by the resistance, divided by 2. Indeed, these two equations play a crucial role in understanding RMS. I hope the derivation process was clear. As you observed, arriving at these equations for AC circuits involved a more intricate path compared to DC circuits. Now, let's compare all the equations we've derived up to this point. These are the methods to calculate power in AC and DC circuits. In AC circuits, we use peak voltage and current. But here's the catch. We can't simply plug these peak values into the same formulas we used for DC circuits. We have to derive separate equations for AC, as demonstrated here. This requires additional effort. So, ingenious engineers attempted to define effective voltage and current values to represent AC systems. These values allow us to portray AC systems in a manner that aligns with the same equations used for DC circuits. We're employing a simple trick here. Assuming the resistance in both circuits is the same, we consider the power produced by both circuits to be equal. By utilizing equations 1 and 3, we can determine the DC circuit's equivalent voltage value for the AC circuit. Similarly, by using equations 2 and 4, we can ascertain the DC circuit's equivalent current value for the AC circuit. Using this DC circuit analogy makes calculations in AC systems more straightforward. These values derived are commonly known as root mean square values for AC systems. Almost always, RMS values are employed to express the voltage and current in AC systems. If your household voltage is 120 volts, this represents the RMS value of your domestic AC supply. Using our equation, you can determine the peak voltage of this supply, which amounts to approximately 169.7 volts. Alternatively, if your domestic voltage is 230 volts RMS, the corresponding peak voltage can be calculated using the same equation, resulting in an approximate value of 325.3 volts. That's all for today. If you think my contents are valuable to the world...
All right, so I was a little off. I said it was 140 volts that came out of the wall, but it's actually more like 160. Crazy stuff. But that was, again, a long explanation for why we have this association between average and maximum that I really want you guys to know and understand and be able to use, okay? All right, we're gonna pause there. Let's do a 10-minute break back at 3:50, okay, and we'll keep chugging.